Hello, my name is Joseph Liserio. My research project is the use of layer protection losses and system integrity levels for the enhancement of process hazard analysis in petroleum refineries. A little bit of project background. Petroleum refinery industry is covered by the OSHA Process Safety Management Standard. Underneath this standard, a major element is process hazard analysis. Now, most refineries use HAZOP, Hazard Operability Studies, HAZOP, to comply with this PHA element. Now, HAZOP is a qualitative PHA method. So a lot of refineries and other industries are uh, using layer protection analysis as an enhancement of their PHA method. And layer protection analysis is a semi-quantitative method uh, that's used in both the refinery industry and other industries to enhance the PHA studies. And the reason why layer protection analysis is an enhancement of a PHA is because it better identifies the need for additional risk reduction. And this is based on the acceptable risk reduction criteria and independent protection layers. So the objectives of my project. The first objective was benchmarking of the risk tolerance criteria adopted in the petroleum industry and doing a statistical analysis of any collected data. The second objective, and probably the most important objective, is a comparison of PHA scenario performed without LOPA using the HAZOP methodology, qualitative method, and comparing that to a similar scenario and analyzed with LOPA. And the reason I'm doing this is to determine if there's any significant difference on whether LOPA analysis is able to identify the need for additional risk reduction. And part of this objective is, of course, comparing the initial HAZOP performed without LOPA and then compare with those performed with LOPA. And I did a t-test, was performed to test if any significant difference exists in LOPA identifying additional risk reduction. So what I'm looking for is whether or not the mean for the risk reduction identified using LOPA is greater than the mean for risk identified using HAZOP. My third objective was determining if there are any factors that can predict the type of independent protection layer or protective device to close the gaps for SEAL 1 to SEAL 3 LOPA gaps and the related costs. So I did. This was performed using a single multiple variable regression model, which were developed to determine what factors affected the selection of certain independent protection layers. And when I'm referring to independent protection layers, is basically a device that increases the risk reduction for a particular scenario or hazard scenario. Some of the factors that were studied during the project research was process unit, type of equipment, the type of initiating event, the seal required to close the LOPA gap, and the type of scenario involved in the HAZOP study. And a variance distribution and standard deviation for IPO costs were also included in the research project study. And these three objectives were enabled to provide knowledge and data on how LOPA can be used in the petroleum refining and other industries to enhance their PHA studies. And by doing that, they are also reducing the serious process safety risk to a tolerable level. All right, the first objective, the materials and methods for objective 1, which is benchmarking the risk tolerance criteria. A survey was sent to 10 different companies who are a member of the U.S. National Petroleum Refining Association, and requests were made for information on the risk tolerance criteria that they use for LOPA studies. And the data was collected to determine the following: the frequency and distribution of data, and any mean, mode, standard deviation, or variance of the data. The second objective, which is determining if LOPA is significant in identifying additional risk reduction in comparison to the typical HAZOP study. For the same companies that were requested information on the risk tolerance criteria, also requested heads-up study data from their survey companies. A lot of companies were reluctant to provide this information because they were concerned about the confidentiality of the data. So in the part of the study, of course, no company identification or identifiers was used to keep the confidentiality of the data. Uh, Once the data was collected, then I categorized the data by several factors, which include process units, type of equipment, the type of scenario, and the initiating event. And then we looked at the risk reduction difference in pair HAZOP studies. And when I say pair HAZOP study, I'm talking about a LOPA study and a HAZOP study. So once we collected the information, categorized it, then we did a mean standard deviation variance for the following. So first we identified was any risk reduction identified by the HAZOP analysis team, which we call SEAL HAZOP. Then we looked at the risk reduction or SEAL level identified by LOPA analysis, which we would call SEAL LOPA. And then we looked at the difference between the SEAL values, which are just the amount of risk reduction required between the two analyses, which is what we call the SEAL difference. And then a t-test was done between the means of SEAL HAZOP and SEAL LOPA at a 95% confidence level to determine if LOPA had a significant difference in identifying any additional risk reduction. And our third objective, which include factors and costs for selected SEAL devices, we categorized the collected data from the HAZOP studies that had identified LOPA gaps. In other words, HAZOP studies that identified the need for additional risk reduction. And so, for those type of scenarios, we categorized by the process unit, the type of initiating event, the HAZOP deviation, the SEAL required, which is the amount of risk reduction required, the type of HAZOP scenario, and then finally the dependent value, which is what we're trying to predict, is the type of IPL device. All right, for the third objective, which includes the factors and continuing, so we're based on all the collected data. Once we categorized it by all those different factors, then we developed a single multiple regression modeling. Was conducted using what we call indicator dummy variables, using statistical technique. In this statistical technique, basically, since all the independent variables other than the SEAL required category were in category format, except for the, like I said before, the SEAL required. So each category was coded as 1 when it was present and a 0 when it was not present in the scenario analyzed. So based on this statistical technique, each category was then listed as an independent variable. Instead of each factor being a separate independent variable, each category became an independent variable using this statistical technique, which was required because all the data pretty much was in the category format, other than the SEAL required. We also calculated the mean standard deviation and the costs were calculated for the IPL estimated costs. All right, so here are the results for objective 1. Only 3 data points were collected from the survey, and they are shown right below in table 8. The mean of risk tolerance criteria was 1 times 10 to minus 5 with no standard deviation or variance. So basically, each of the 3 companies that submitted data were using the same risk tolerance criteria for the most highest severity or consequence scenarios. And this value was 1 times 10 to minus 5 occurrences per year. Some companies also use a second tier risk tolerance criteria for less severe uh, scenarios or less risk ranking scenarios. And in those cases, they use 1 times 10 to the minus 4 occurrences per year. So this risk tolerance criteria basically is the basis for deciding whether or not you need additional risk reduction. So if you're doing your LOPA calculation, if uh, you need more risk reduction, then the value that you need would be below the risk tolerance criteria. So the current protection devices, the overall probability of failure demand is greater than the acceptable risk tolerance criteria. So then, therefore, you need additional risk reduction to get it below the risk tolerance criteria level. All right, in objective 2, we had 300 pair scenarios were analyzed for objective 2. And then we did descriptive statistics from Excel data analysis for the seal level for the risk reduction, identified by the HAZOP, which is seal HAZOP, that identified by LOPA study, which is seal LOPA, and then the risk difference between the two, which is we call seal difference. And here's the data for the three seal level differences. As you can see, the amount of seal level or the amount of risk reduction identified by the LOPA study was almost 4 times higher than the amount identified by the seal HAZOP. As you can see, the seal difference is greater than 1, 0.4. And you can look at the minimum and maximum values for the seal HAZOP. The maximum value was 1, so that meant that only a seal level 1 was the identified during the HAZOP study. While with LOPA, there was a seal level 2 identified. Then shown on the right there on table 10 is the t-test between the two means of seal HAZOP and seal LOPA. This was done to determine if LOPA identified a need for more risk reduction in the HAZOP study. As you can see, in table 10, the value for the t-stat is 13.44, which is much greater than the t-critical of 2.4 for a one-tail test. And the t-test was done on a one-tail because the alternative hypothesis was whether seal LOPA was greater than seal HAZOP, the means in. Where the means for seal LOPA greater than the mean for seal HAZOP. That was the alternative hypothesis for the t-test. Of course, both of these have unequal variances. Okay, for objective 3, we had 157 scenarios in which an IPL device were selected to close the LOPA gap. And of course, shown above is an example of the data points shown that we used in the study. As you see in the table, the first 5 columns are the categories or factors that we use in our single and multiple regression model. You see the process unit, there's some examples, some values for the process unit, some examples for the HAZOP deviation, the type of scenario, the type of initiating event involved in the scenario, the LOPA seal level requirement, and those 5 factors were all considered the independent variables in the multiple regression and single regression models. The dependent variable was the type of IPL device that was used to meet the seal target. In other words, the device was chosen to provide added protection for the scenario. And so that type of device was given what we call an IPL number. that was used in our regression modeling equation. So the IPL number became our dependent variable. So what we're trying to do is, can any of those 5 factors shown in the first 5 columns, can they predict the IPL number? And then the costs related to each of these IPL devices based on estimated capital budget are shown in the last column. All right, so shown here in the table 11 is a regression model for the process unit factor. As you see right here on the right side are all the factors in the regression model, all the factors that were, or all the categories that were analyzed in the regression model. So in the process units, you had vacuum flasher unit, crude unit, the FCCCU, which was abbreviation for fluid catalytic cracking unit, the alkylation reforming unit, the hydrotreaters, bulk storage tanks, hydrocracker, acid sulfur plants, and the coker units. So these are the units that were involved in the regression modeling, all the categories. And then the SIL value, which is the only regression model that was not using the dummy variable technique, is shown there. So basically you just had the SIL level requirement was either a 1, a 0, 1, or a 2. Here's some more simple regression models for the other factors that were considered, including initiating event. And then you see some examples, the coefficients and the examples of the factors that were looked at for the initiation event. So you can see a failure of a loop oil pump is the example of an initiating event that was looked at, or which the data fit into a category. Other categories include pump failure, temperature transmitter failure with a valve closed, temperature transmitter failure, temperature transmitter failure with a valve open. So you can see all the factors or categories that were used for initiating event in which the data fitted into. Now the table 14 shows the hazard deviation. So hazard deviation is examples of those are no less flow, more flow, high level, higher temperature, no less pressure, misdirected flow. All right, table 15 is a simple regression model for the last factor or another factor, which is the hazard scenario. As you can see, there were 10 different scenarios that our data fitted into. They're all on the right side of the table there at the bottom right, or I'm sorry, the bottom left. Bottom left of the table shows the 10 factors or 10 categories that the data fitted into for hazard scenario. So after building the single regression models for the 5 main categories or factors that were considered in the study, we did a multiple regression model to determine whether we can get a better model on more than one factor or one category. And so the 2 factors that we selected for the multiple regression model were hazard scenario and hazard deviation. And the reason these 2 factors were selected for the multiple regression model is because they had the highest R-square value, which means that they had the highest correlation or the highest predictability in predicting the IPL number. And so the model here is shown. So the factors that were included in this model included the hazard deviation, which were the first 5 values you see in the left side of the table, which included no less flow, more flow, high level, higher temperature, no less pressure, and misdirection flow. And then below that you have the hazard scenario categories. which included 10 different categories there. And you can see the coefficients, which are the related to the linear regression equation. There was also another multiple regression model that was built that basically we took the 16 factors with the lowest p-values from the single regression models. So the factors with the lowest p-values indicated they were the best predictors of IPL device. So we took them and tried to build a multiple regression model based on those different categories that had the lowest p-values. And the reason why we selected 16 of them is because the Excel data analysis tool is limited to only 16 categories maximum. It just happened to be that the first multiple regression model had exactly 16 values or categories that the model was built on. So it managed to include all the values for hazard scenario and hazard deviation. So here's the equation that was built from the multiple regression model for the with the highest R-squared value, which is the highest, which indicates the highest correlation or the highest predictability in predicting the IPL number based on the factors used in the regression model. And so this regression model, like we mentioned before, is a hazard deviation, hazard scenario, multiple regression model. And the equation there is shown there. So the IPL number is equal to all these different factors with their corresponding coefficients. And as you can see, some of these factors negatively impact the IPL number or positively impact the IPL number, depending on the sign before the coefficient. So, for example, for more flow, you see that it has a minus 2.73 effect on predicting the IPL number. And for a positive would be I, which is the scenario of flame out of gases in the heater, resulting in potential reignition of gases and fire explosion. So that would have a factor of 0.7 plus 0.78. So here's the descriptive statistics for the IPL costs, which are shown on table 18. As you can see, the average value for the IPL costs came out to about $26,634. So that meant for each device that was used to close a gap in the amount of risk reduction, the average price was around $26,000 to close that gap. But there is a wide standard deviation in this statistics for the IPL cost, which was at $47,480, which is very high standard deviation. And as you can see, the variance is very high also for this for the IPL costs. All right, so just discussing the results for Objective 1. Only 3 data points were collected, and all of them at least for the highest scenarios, for the highest risk scenarios, they all had the same value of 1 × 10⁻⁵ occurrences per year. For lower, less severe, or lower risk ranking scenarios, 2 of the companies used a lower risk tolerance criteria of 1 × 10⁻⁴ occurrences per year. Basically, we needed more data to be able to make a more higher level of statistical analysis with high level of confidence. With using only 3 data points, we couldn't really come up with a high level of confidence in our data. For Objective 2, you can see the averages for the identified risk reduction, which is corresponding to the cell levels. So cell level 1 means that you need a 1 times 10 to the minus 5 additional risk reduction. If it's a 2, it's 1 times 10 to the minus 2 additional risk reduction. And then if it was a cell 3, then you needed 1 times 10 to the minus 3 additional risk reduction. So just based on that, the average cell level reduction for the HAZOP study was 0.0167. And if you compare that to the amount of risk reduction identified by LOPA, it was 0.423. So there's a big difference in those averages, those means. And the average risk reduction difference was between the cell LOPA and cell HAZOP was 0.407. So that's a positive sign. So that means that cell LOPA identified more need for additional risk reduction far greater than the HAZOP study did. So the HAZOP team, the scenarios that were just analyzed using HAZOP only 5 of the 300 scenarios required additional risk reduction. In comparison, LOPA, over 125 of the 300 scenarios identified the need for additional risk reduction. So that's a huge difference in the amount of additional risk reduction identified by LOPA compared to the typical HAZOP study. So the t-test between the two means indicated that the alternative hypothesis, which is that cell LOPA mean is much greater than cell HAZOP, is true because the t-stat was much greater than t-critical. So we can reject the null hypothesis that the two means were equal and accept with a high level of confidence, which is indicated by the extreme low level for the p-value of 1.46 times 10 to the minus 33. So a very high level of confidence we can accept that the mean for cell LOPA is much greater than cell HAZOP. So based on that results of the t-test, we can definitely say that LOPA identifies much more the need for additional risk reduction in comparison to a typical qualitative HAZOP study. So basically, we're accepting the alternative hypothesis that the cell HAZOP mean is much greater than the cell HAZOP. All right, for the third objective, the R square values, which kind of indicates whether or not a factor is a good predictor of the dependent variable, which in our case is the IPL number. For the 5 individual factors that we looked at, they were all poor predictors of IPL device number. All the R square values were less than 0.35. For the R square value for the multiple regression model, for HAZOP deviation, HAZOP scenario, indicated a modest predictor of IPL device. The value there was 0.438, which is much better than the individual factors regression models. All the normal probability plot indicated a linear relationship existed between the dependent and independent variables. Dependent being the IPL number and the independent variables being the different factors that we looked at. One of the drawbacks using the Excel as your analysis tool is that we're limited to a maximum of 16 independent variables. Since we're using a statistical method that involves setting up each category as a separate independent variable using the dummy variable technique, we had over 49 categories that were available as factors to be looked at or to be used in our regression models. But we're only limited to using a maximum of 16 in our regression models. So this table 19 shows the different R-square values and F values for the independent variables, which are shown on the left side of the table. As you can see, the biggest, the model that gave us the highest R-square value was HAZOP deviation, HAZOP scenario, multiple regression model. And then, of course, the 16 factors with the lowest p-values also gave us a pretty good R-square value of 0.414. But you can see the seal level was the worst regression model as far as predicting the IPL device. It only had R-square value of 0.081, which is a very poor predictor of IPL device. The IPO costs they range from 5,000 to 2,500, 250,000, with an average of 26,634. So you can see there's a wide range in the IPO costs. These costs were basically estimated capital budget costs, not the actual costs that were where the device installation actually costs. These were just estimates that were used for the capital budget development. So, and you can see the estimation, and there's a wide variance. The sample deviation was over $47,480, which is very large compared to what our average is. So you can see there's a wide variance in the IPL costs. So 68% of the costs were below 74,115, and 95% were below 121,596, which is much greater than our average of 26,634. So the data indicated a wide variance in the IPL costs. So in conclusion, based on the limited data that we have for our first objective, there is a pretty uniform use of the risk tolerance criteria used in LOPA studies in the industry. With the value of 1 times 10 to the minus 5 occurrences per year being used for the high severity risk ranking scenarios, and a 1 times 10 to the minus 4 for lower severity risk ranking scenarios. Of course, this is based on a small amount of data of only 3 samples. The biggest conclusion out of the study is that there is a high confidence level exceeding 99.9% that LOPA does identify the need for additional risk reduction in comparison to typical HAZOP studies. And this, of course, is based on t-test results for the differences, the means for the seal values for HAZOP and LOPA studies, and the average value for the risk difference between HAZOP and LOPA studies, which is 0.406. So one of the biggest findings from this research project is that LOPA is a very good technique in identifying the need for additional risk reduction for an HAZOP scenario compared to a typical HAZOP study. So there is a very much enhancement that LOPA provides for a process hazard analysis. You're less likely to miss a scenario that could result that may have an unacceptable risk and that needs to be addressed with additional risk reduction than would be with using a HAZOP study. All right, the 5 factors that we use to predict the IPL device IPL device number for the chosen IPL device, which included the process unit, type of ignition event, HAZOP deviation, HAZOP scenario, and the seal required. None of them were good predictors individually for the type of IPL device chosen. Of course, this conclusion is based on low R-square values for each of the regression models, which were below 0.35. But the multiple regression model using HAZOP deviation scenario is a modest predictor of the type of IPL device chosen based on R-square value of 0.438. And finally, the IPL device costs have a wide variances with an average of 26,634 and a sample deviation of 47,480. So this indicates that there is a large amount of estimation error in the IPL cost data, which were based on estimated capital budget costs. All right, some recommendations from the research study include that we need more data for the risk tolerance criteria so we can get a better, more accurate, and higher level of confidence in the accuracy of the data. One of the drawbacks, of course, companies are very reluctant to share this information outside their organization. Another recommendation, basically from the results of the study, definitely I would recommend that LOPA should be used in addition to HAZOP in process hazard analysis studies to ensure that the required layers of protection exist to reduce the process safety risk to an acceptable level. So definitely LOPA is a very powerful tool in identifying whether or not your risk for a typical scenario, does it have adequate protection or not? Or do you need more protection? And LOPA is a very good tool in identifying that need or making that decision whether or not you need additional protection devices to reduce your risk to a hazardous scenario from occurring. And in order to build a better multiple regression model, uh, using a statistical tool that can perform a regression model with more than 16 variables would be very helpful in this. I think being able to use more than just the 16 factors that were used in the hazard deviation and the hazard scenario multiple regression model, we could use more other factors. We could have been maybe build a more robust model with a higher R squared value and a higher level of predictability for the IPL device chosen. And based on the wide standard deviation for the IPL costs, it'd probably be better just to get more accurate and actual cost data for in order to get a better or more accurate uh, average for the IPO cost estimates. And attached here are my references, and that concludes my discussion on my research project. Thank you.